Anything you want to ask? Or everything is fine? Did you people solve that question which we were solving yesterday? Did you solve the question which we were solving yesterday?
Yes, sir.
Yes, sir.
You got the answer?
Yes, sir.
Uh, okay. So anything you want to ask in that? Any doubt in this one? Whatever we covered yesterday or day before that? Hmm? You want to ask anything in that way, or shall we continue? So, good morning. So, in the last class, we were talking about how to find acceleration actually, acceleration of fluid field. So, you identify two things based on your velocity vector or flow field. You calculated two things is dimension of flow and type of flow also means whether it is incompressible or compressible by using your continuity equation just to validate that whether you have 2D flow or 3D flow or whether it is incompressible or compressible. So you can use that continuity. Once you calculated that, after that you calculated the acceleration of fluid particles at a particular the location. So this is also the important point in case of flow of fluids in pipeline or in some area. So there also you are the interested, what is my acceleration here? Or acceleration will provide this force and then you can calculate what is the pressure force available there or velocity field. So those are also desirable actually in the pipeline. So acceleration have two terms. One is convective acceleration. So this is term here. Other one is local acceleration. So that is due to actually could be or pump or fluctuating of flow actually. So this will provide you the local acceleration, something which is time dependent part. So moving ahead actually, so what you have there. So then you calculated acceleration of the particles. So in previous equation here, you can use entire velocity vector and whatever will come from here, that would be the total acceleration vector of the particle. So suppose you want to calculate individual component, what is the acceleration of particle in x direction, in y direction and z direction. So in that case, if you are calculating for x direction component, your velocity vector has been replaced by x component of velocity only. So previously here was v vector, so that you have the replaced by x component of the velocity here. So this is u here, this one is also. So the v vector is the replaced by u only. Same thing for y direction actually. So there your v vector is replaced by v actually, it's small v. So that is the component of velocity in y direction. Same thing for z direction there. So your v vector is replaced by w. And then based on velocity vector available to you, actually you will calculate all these component, and then you can calculate their magnitude by taking the means the square root by adding them actually. Okay, is fine. Hello. Hello.
Yes, sir.
Previously we did actually your continuity or mass balance in differential coordinate system. Now we want to do the momentum balance, or you can say the force. We want to also have the force, because these are two fundamental actually quantities that need to be conserved first. So first is mass, then you have force, then after that you have energy actually. These are three things which are always needed in case of any flow or any the material or any sort of conversion or transportation. These are three important ones. Then you have later on some other part also, means entropy and angular momentum principles. So you have those part later. So here we will do the momentum balance, and in differential coordinate system. So here we are taking again a rectilinear coordinate system x, y, z. You have a differential volume, differential of dimension delta x, delta y, delta z, as previous one, same thing. Only thing now here we are considering actually in terms of forces actually. So what you have here, what this have six surfaces. So forces can be applied only on the surface, fine. So let's say at the center of that you have some amount of force, let's say sigma xx. Why have I put the sigma here? I can tell you later. You can actually this is actually some sort of the stress actually. Each force on any system would create some sort of the stress. If it is parallel to the surface, it will create the shear stress. It will try to drag it, or it will try to drag it with this. Like this, you have a hand, you have this bottom palm, you want to move it, so you want to drag this both the palm actually. So that's called shear. Sometimes you can have a perpendicular to this way, so this force will try to compress it. So you will have compressive force here, that will become pressure actually. Okay. Sometimes you will have a force just to stick it and try to drag it outside, so you want to stretch it. So that is again some sort of a pressure actually. So that you can say some sort of system under pressure type of thing. So inside of the system you have a pressure, and it will try to expand your body, just like your gas cylinder. So you have a pressure inside the gas cylinder, it will try to expand the things. So it will give in that part actually a pressure just to expand it. Okay. So in that way, so whenever the force normal to the surface, it will give a pressure component, or pressure component, it would be in two way, either compression or expansion way. When you have parallel to the surface, then it will give a shear force. It will try to drag the thing, it will try to make them flow. Is that fine till here? How these forces will act on the surfaces? Is this fine?
Yes, sir.
Right.
Yes, sir.
So as case of previous one, so let's say the center of this control volume is also O at the center, which is you cannot see here, it's not mentioned here. So let's say center is O. At the center, you have considered that x direction component of your shear is actually sigma, y direction component is tau yx, and z direction component is tau zx. So you might be confused that one place you are taking tau, other place you are taking sigma. So the question is that if you are doing the balance only in x direction, here you see everywhere you have x here. Here you also have sigma xx. Here you have tau yx. Here you have, I can, maybe in this way you can, I can draw the arrow here. So what you have, let me, so see in this case, here you have tau by x. So what this tau by x is, you are doing shear, y is the plane and x is the direction, because that's what we have taught the time I have explained you the Newton's law of viscosity or shear force. There we wrote tau by x. So the first component is plane, second component is direction. So in this figure, we are doing all balances in x direction only. So therefore, we wrote here, here actually this tau yx. What is this tau y? This is practically a bottom one, bottom surface of, let's say, this of the notebook. You are doing bottom. So bottom may or top, your perpendicular will go either in plus y or minus y. So your plane is y. Now you want to do the balance only in x direction. So your plane direction is x. Therefore you wrote tau yx. Either you write for bottom or you write for top. You will become tau yx. Is that fine? Because plane is y, because the perpendicular will go to the y direction, and you are doing balances only in x direction part. So that's what I wrote tau yx. Is this fine? Any response? Hello? Hello?
Yes, sir.
Is anybody there? So did you understand why this tau yxm? So if you are on this plane or is bottom, the perpendicular will go to the y direction. So that is your plane. Now you want to do the balance in x direction, so you have put tau yx. So that's what you wrote for top, this tau yx plus del tau yx upon del y dy by 2. Then you wrote bottom tau yx minus del tau x upon del y into dy by 2. Because tau yx, your magnitude of shear stress at actually you're the center. So from Taylor's expansion, you got delta y2 on top, delta y2 on bottom. So same thing we did in case of mass conservation part. Is this fine for top and bottom component? This one and this one? Is this fine for this? Somebody should respond
Yes,
to me,
sir.
right? So that is for top and bottom. Now you think for this side. So this side is your x coordinate. So let's say this side is your x coordinate. So here perpendicular drawn will go to x side. So therefore you have here x. Now you also do the balance only in x side. So your both coordinate here at this particular points are x. Okay, both coordinate are x. Your direction of plane is also x. You want to do the balance is also in x direction. So you have here x. So where these things are same, x, it will become normal stress actually. So normal stress is defined by term sigma actually. And parallel stress or shear stress or parallel to the surface are defined by tau. That is called shear stress. This is called normal stress. Okay. So now this tau sigma xx by the quantity at the center. So you went dx by 2 to this side. So you wrote here tau sigma xx plus del sigma xx upon del x multiplied by dx by 2. This is for this side. Right side, same thing for left side. So you are going to minus side of that. So you have the subtracted that quantity again. So this is for your x direction component, x plane. Now let's say z plane. This is your z plane. So here perpendicular will go to the z direction. So therefore you wrote here this quantity here is, this one is tau zz. Okay, tau z, that is the plane. Now direction you want to do balance only in x direction. Therefore you wrote here tau zx. Okay, so this side, if you are going to front side, that is your plus side. If you are going to back side, that is your minus side. So this side is minus here. That's what here you have. This side here is minus. Here you have tau zx and minus tau zx del tau zx upon del z into dz by 2. So is this fine till here, that how have we defined this plus minus and tau zx, tau yx and sigma xx? Is this fine till here? Is this fine till here?
Yes, sir.
Yes,
Right?
sir.
So that way we have defined. Now these are the stresses, means force per unit area. So if you multiply by area, you will get a force. Correct or not? So
Yes.
in this case, let's say for this in x direction, so area for this would be this dimension and in this one. So this is your, let's say this is your delta z and this is your delta y. So that is the area. So tau xx, this term should be multiplied by your delta y, delta z. So you will get that is the force. So let's see what I have on next slide. So next slide is this. So what you have here, so we are doing here rate of linear momentum change is called actually your force. Rate of change of the momentum, linear momentum is called force, right? That's what is being taught to us from 9th standard onwards. Now, linear momentum would be calculated by velocity into mass. So that's you have here. So let's say you have the several masses there. So you have differential mass, add them, all of them, and you will get a total momentum of the system. Fine. Now, force can also be defined in this way that differential force is also called mass into acceleration, right? So you have here differential mass dm. Acceleration is already taught to you, that is the dv upon dt. So if you know the velocity vector and just find dv upon dt, so that is your acceleration. Now mass of the particle could be its volume. So volume was dx dy dz multiplied by density is your mass. And this velocity vector you already know, and how to calculate acceleration from that. This is the expression for to calculate acceleration of the particle. U del v upon del x, v del v upon del y, w del v upon del z, and here del v upon del t due to local acceleration part. So that is your acceleration part here. Okay, so you got force from here. Now, if you want to write this is force vector dff. So if you want to write for x direction, so your velocity vector here would be replaced by u. So here you say this is also u, this one is u, here is also u, here is also u. So you got x component of means force. Same way you can write for y component. Here your v is the replaced by v, actually the v vector is replaced by small v, is the velocity component in y direction here. So here also, this one also, third term also and fourth term also. Same way you can write for z direction. Fine? Is this fine? Hello?
Yes, sir.
Right. Now, these are the forces because we have drawn the figure, and now we want to do the balance only in x direction. So all the forces there, the means the stresses given in previous column was only in x direction. So suppose we want to add them up. So this was the component which was going in this side. Here, how do we make them plus or minus? That we have to see. Why is it plus or minus? Okay. Direction we have considered this. Fine. So in this case, if you say for first term, this is the magnitude and this is the actually your plane. dy and dz is the area. So both the things are in the same side, same direction actually. Area vector would also be this way, and direction of sigma is also considered that way. So both are in same direction, therefore this is plus. In left side, this direction is fine. We have considered this side. Now area vector is going to this side, so therefore this term is minus here. So therefore, same thing we did in case of mass conservation part also. Same thing we are doing here. So this is for x direction component. This is for biplane. This is for z plane. So we have added all of them. That's fine till here. So somebody should respond.
Yes, sir.
Okay, so here this side we have taken all these stresses at the center. One is going x side, one is going y side, one is going z side. That direction we have considered. Now wherever this direction and planes are in same direction, that is plus. Wherever they have in different side, that is minus only. So therefore we did this part. So now you add them up and let's see what is coming. So if you add them up, you will get this, the sigma xx upon del x, del tau yx upon del y, del tau zx upon del z. So this is your x direction component. So these are your all surface forces. These are acting on the surface. Now surface force is not only force. This particular control volume would have its own mass also. That is called body force or body weight. Body weight practically acts in the downwards, so we are just considering its component in x direction. So how would I calculate that? If somehow I know its mass, so if I can multiply the component of g in that direction, I will get the body weight component in that direction only. So therefore I did the same thing here. The body weight component in x direction, if I know mass, this rho into dv is your mass, multiply by gx, the component of g in direction x. So if it is completely horizontal, so gx would be 0. Inclined, you will have some value of gx. Okay. So therefore we are putting gx, the component of g in direction x. It may be 0, it may be non-zero, it may be some sine cos theta something, g sine theta, g cos theta, depending on orientation of the object. So therefore we put here term gx. So you got rho gx dx dy dz. This is your body force. Now you have all forces because a particular system can have two component only, a body force or a surface force. We are not considering any electrical force, any magnetic force or any other forces. No, we are not considering any other forces. We are only considering these two forces, the body force and surface forces only. So if you want to calculate net force in direction x, dfx would be d f sx, the surface forces in direction x, and body forces in direction x. This we already got from your mass into acceleration part. So this is your f equal to ma part. So this is your m, this is your acceleration part. This is your right side, the total force which you are calculating from here and from body force. So if you substitute that, finally you got this equation actually, the rho u del u upon del x, v del u upon del y, w del u upon del z plus del u upon del t equal to rho gx and plus del sigma x upon del x, del tau yx upon del y, del tau zx upon del z. So this is your force balance in direction x. Okay. Same way we can write for direction y. If you want to write for direction y, only this this particular term here, this u would change by v. Here also it will change by v. Here it will change by v. Here also it will change by v. This gx would change by gy. Here this last coordinate here would change by y here. So you will have xy here. Here you have yy. So now the coordinate would become same. So then this tau would become sigma actually, where the both plane and direction are same. Your tau, which is the symbol of the shear stress, would be converted to the sigma, then it will become a normal stress actually. This will become zy. So we can write the equation for that. This is equation for x momentum, which we have write just now. Now same way we can write for y and z direction. So y direction is this equation here. So you have this u has been replaced by v actually here, this point also, this third point, fourth point. Here gx has been changed by gy. Here this second coordinate has been changed by y here, here also y, here also y, here also y. Okay, same thing for z. So if you will try to drive it, would it be possible to you drive these three equations? Would it be possible? What happened today? Nobody want to respond? Hello?
Yes, sir.
What happened? Nobody wants to say anything. What happened?
Sir, my neighbors have a marriage in their house.
Okay, you would have the marriage, but what about others? Everybody will not have marriage. Now, so after that, now let's say we are considering for a Newtonian fluids. So Newtonian fluid, I have given your chapter 1 there where we are talking about fundamental or fluid properties. So where I told you there that tau yx is given by mu del u upon del y, right? Now here, because velocity here you have 2D planes or 2D, so you will have x component of velocity also, y component of velocity also. You have both the component of the velocity. So your tau x would be given by this term here. You will have two term here, del b upon del x, how this y component of velocity is getting changed in direction x. Another thing is del u upon del y, how this x component of velocity is getting changed with respect to y. So this would be your net shear stress in direction x actually. Okay, so you wrote tau yx or tau xy would be this only, mu del b upon del x plus del u upon del y. Same way you can write for tau yz. Now you are talking about the motion in yz plane. So yz plane or zy plane both are same. So you can write mu del v upon del z and del w upon del y. Same thing for zx plane. So for zx plane, you will write tau zx or tau xz would be mu del u upon del z plus del w upon del x. So these are stresses in all three directions actually, or you can say individually in x plane, y plane, zx plane. So you have expression of tau. Now you need expression of sigma, the normal stresses actually. So normal stresses are given by this, and there is a derivation for that, but for time being you consider it actually. So you can find it, or I can give you the detailed derivation of these two also. So sigma xx is given by this minus p is thermodynamic pressure actually. This is 2 by 3 mu del dot v. This is actually due to this actually fluid dilation part. Then plus 2 mu sigma also, this is due to the motion of this fluid viscosity. So these are coming from there. So derivations of these are also there. So time being you consider them that as it is only. So here you have again sigma pi is given by this equation and sigma zz is given by this equation. So all in previous equations where you did the force balance here now you know everything, right? Now you know the sigma xx, now you know the tau yx, now you know the zx. You have everything. Now substitute them. Okay. So why we are converting these thing all in velocity? They're doing that because we don't have any just to measure the stress on a fluid or on a particular element. The easiest part for us is just to measure a velocity. Velocity we can measure. We have a flow meter, we have a pitot tube, which gives the velocity at any point. So we are converting these uh, equations into a variable which can be measured directly because these stresses cannot be measured directly. So we are converting these equations into a measurable quantity which measure directly only. So for that reason only we wrote your shear stresses in terms of velocity. We can before we can measure them easily. Same thing, these shear stresses is also in terms of thermodynamic pressure, viscosity, and your velocity components. Okay, so these all can be measured easily only. Now the substitute all of them back into previous one. So if you do that, so these equations will come actually. Substitute. If you will substitute everyone, you will get this. Now I want you to do that. Just everybody take out there the notebook and try to substitute there. In this equation, take this one, substitute the value of the sigma xx, substitute the value of tau x, substitute the value of tau zx, and let's see what is coming. Just solve only this side only, left side one. Left side would be as it is because that is not going to change. इसको simplify करिए. Everybody should take out the notebook and do it. Take out the notebook and do it. Are you doing or not? Hmm? I'm asking just to simplify only this part. This part would be as it is. No need to solve that. Just focus on this part only. Can I hear anyone who is solving or not? Hello? I can't hear anyone. Is anyone present or everybody went away by signing in? Will anyone respond something?
Yes, sir.
So much time to respond. Anyway, career, just do it. So you have this also the substituted. So let's write what is the next equation from here. We'll write that what will you get from first equation would become your differentiating that with respect to x. So first quantity your there is p there is coming with minus sign. We have this also. So this you can write maybe as it is here with minus sign and put this inside the bracket, and here you can put your term del upon del x. So this is this one. Now for this term you have 2 mu is a constant, so which is not going to change anything. You have a square, so you will get a square here. So you will get a 2 here. Here also you get power 2. Faster than me, I am to just doing the mean don't for my thing, because just keeping the idea and just do something. Do it faster because you are doing on pen and paper. You can do much more faster than me. So here I can put again square, and this also square here. Whoever has completed this will immediately tell what they have got. So here you have y. So that y. Now this side, first set. So you can rewrite again. So if you rewrite what will come from here, let's rewrite something. Whoever has completed, just inform me so that we can check it. What have we got? These two mu terms can be taken out from here. It would be here. Now from here, you have square and square everywhere, so we can club them together. So this I can add them at this particular case. Here I have this is places here, so I can write it 2 times mu square u upon del x square. So I can write it here, this one at 2 times. So one time I wrote here, another time I can write at this particular place. I just wrote it two times, but they are here twice, so I wrote 2 times. One time with them, one time this here. At this place, square means you have this term is again 2 times, so I can write it 2 times this again here. I'm just changing it for 2 times here, so you got here del x del x. Now I can write again same equation, so because I want to solve it. So if I do that again, so I have this term. So from here I can take this mu common. This mu is taken common here. I can write this entire thing inside a bracket here. So I have taken mu common from this one. Let's say what can I do from here? So I have del del square upon del x, del square upon del x. So everywhere I have del square upon this, right? So I can take that part also common actually from here. So if I take that thing common from here, let's see what is coming. So if I write, let's say something here inside bracket, and from here I'm taking a term common is, let's say I'm taking a term mu is also common because viscosity for a incompressible fluid is currently we are not making constant, so we are taking constant viscosity actually. So now we have here one term here, del upon del x also we want to take common. So taking that only common here. So if you take common here, I will just get this one. Inside the bracket, I have already taken del upon del x common, so this square and from here also will go away. And here also one x will go away. So I will get this. At this place, because I am taking del upon del x, so I will leave here del b upon del y. I will leave with that term here. So I will get here at this particular term. This term will go away from here. I will get with this term here. Here also viscosity I already taken common. So this one will also go away from here. I will get this. Yes. Anybody is getting something or you are watching me? Now, does anyone remember what is your continuity equation is? Anyone? Any volunteer for that? Continuity equation, what continuity equation is? Anyone can tell what should I write for continuity? What is continuity equation? Hello?
Sir, del by del T over control volume rho dV.
plus.
Or, okay, just wait. So you are getting or I can find from there because that may save my time actually. This is what we have now. Yes or no? यही है. Hello. This is what we have derived already, right? Continuity equation for incompressible fluid. Yes or no?
Yes, sir.
Right? So you have here del u upon del x, del v upon del y, del w upon del z, which can be rewritten as del dot v vector equal to 0. This is your continuity for incompressible fluid. So I can write same thing for that also. Where were I? Equation कहाँ गया? In my equation, which we were typing. Where that might have gone? We are typing something. Here? No. But that must be there somewhere, right? So, that gone somewhere here? No. So, I don't know where that gone. Can I open this math? No, it's blank. So anyway, so we were solving this only, right? So we have the substituted, not this one, where we were solving. So we were solving only this one only. We have the substituted that, and finally you have, so from here, this is your continuity part. From your continuity, you are getting del dot v vector equal to 0. Yes or no? So by putting that, you will get this equation back. V somewhere here only in this way. So we already got this term here. Here you got a term. Tell me what was the term here? Anybody did something or not? Nobody has done anything. What was the term here? So not responding. Okay, it's just closing the class. Fine. Fine, then we will end up here.